Welcome back. Now we're going to move into chapter 7. You can see we're all done with Avogadro's number, converting grams to moles, moles to grams, and even grams to atoms and molecules. You have a good handle on percent composition, along with empirical formula and molecular formula. So the most important part of this unit actually is called stoichiometry. And that's a big word. That's a long word for basically the study of chemical reactions in terms of mass changes. And you can see it's on page 316 to 320 of our text. What I've got here is an example of a reaction that we've done before. You may remember I put some sugar into a test tube containing potassium chlorate. It decomposes very quickly and it makes potassium chloride and oxygen. The equation's balanced there as well. Well, what does the mole really have to do with chemical reactions? That's the question that we're going to answer over the next couple videos. Firstly, according to our equation, you can see that for every 2 molecules of potassium chlorate that react, we only get 2 molecules of KCl and 3 molecules of oxygen. Now, the truth is we can't see molecules. They're not very useful to us in the lab. So as chemists, we're going to use the mole because we know that a mole of anything is 6.02 times 10 to the 23rd particles. So in a sense, the number of moles involved with each species in this reaction is the same as the number of molecules. It just makes sense to work in moles. So with that in mind, the equation tells us, and of course it is balanced, that for every 2 moles of potassium chlorate that we decompose, we get 2 moles of potassium chloride and 3 moles of oxygen. Now, you might be sitting there going, how can 2 be equal to 2 plus 3? And I gotta say, this is one of the big conundrums that I dealt with when I was in grade 11 chemistry. The answer is very simple, however. Moles are not conserved in chemical reactions. What is conserved is grams. And the law of conservation of mass and energy that you learned in grade 9 likely tells us so. So when we really look at this equation, you can see that if we use the molar mass of potassium chlorate, we've got 2 times 122.6 grams ends up being 245.2. The molar mass of KClO3 is 122.6, and because there's a 2 in front of here, we have to multiply it by 2. So for every 245.2 grams of potassium chlorate we begin with, we get 2 times 74.6 grams of KCl, which is 149.2 grams, and we get 3 moles of O2, which is 3 times 32, which is 96. And very interestingly, when you look at 245.2 on the reactant side, if you add that to 149.2 and 96, they're the same. This, like I said, is because of the law of conservation of mass. So that's what stoichiometry tells us. It basically gives us a look at the mole ratios in chemical reactions, but even more importantly, because we work with grams in the lab, we want to be able to weigh out reactants and products and see how our reactions went. So all of these things, whether we're looking at the molecule level, the mole level, or the mass level, all say the same thing. And from here, we're going to build on the study of stoichiometry by looking at moles first. We'll look at questions that involve moles to moles in ratios. Then we'll look at moles and grams together. And finally, we'll look at mass and mass together. That will become crystal clear as we work through some of the lessons that are yet to come in Chapter 7. So a little introduction to stoichiometry. Hopefully it makes a bit of sense considering you've already made it through chapter 6, relatively unscathed, and we'll continue on with our stoichiometry journey as we go.